All right, welcome to the webinar for the month of May 2019. We're talking about Bluetooth Low Energy, Locationing 101 today. This is definitely a 101 webinar. It's an introduction to the concept of location tracking and how it can work with Wi-Fi in general, with Bluetooth Low Energy, with any RF-based system, really. So there are ways that you can do locationing simply based on an RF signal. And so these are used by different systems, including BLE. Now, what we present here today is an introduction to this concept. There will be more information in our materials for study for the new CWSA certification that's launching on September the 1st, as well as other certifications that follow in that track in the future in what I'm kind of calling the rest of the rest of the wireless world track. So our current track, CWNA, CWSP, CWAP, CWDP, and CWNE, and even really CWS and CWT are very focused on Wi-Fi. So Wi-Fi is the driving focus. Other wireless technologies are alluded to from the perspective of how they impact Wi-Fi and how your Wi-Fi has to maybe coexist with them a little bit, but not great detail on how they work and operate. The new track that we're starting with CWSA, the Certified Wireless Solutions Administrator, is focusing on those other wireless technologies. In there'll be a little bit of Wi-Fi, but it's mostly about other wireless technologies and technologies that help support wireless systems in general, such as APIs and scripting and automation and things like that. And there'll be several certifications in that track down the road in the future, ultimately leading to a certified wireless solutions expert, which will be kind of a sister certification to the certified wireless network expert in the Wi-Fi world. So just to give you some information, there's more coming. We'll do more webinars in the future going deeper into these technologies as well. But we always like to start when we talk about a new technology with kind of a 101 level, an introduction to the concepts. And that's what we're here to talk about today. Now, before we get too far into today's presentation, I do want to remind you that Wi-Fi Trek 2019 is coming up in Nashville, Tennessee. The boot camps, the training before the conference is the 15th through the 17th, and then the conference itself is the 18th through the 20th. We're about 121 days away. It's that close, so it's coming up very quickly. And of course, you can always learn more at trek2019.com. That's TREK2019.com. So the agenda for today, real quick, we'll do a Bluetooth history, get an understanding for where it came from. Then we'll talk about, BLE. It's more than locationing, but locationing is a big part of what it's used for today. We'll talk about different locationing methods, and then I'll give you some tips that matter. In later webinars, in our materials for studying for CWSA and other future certifications, these tips that matter will be explored in full detail. Why they matter, what all the technical reasons are behind it, and I'll begin your thinking on that today as well. So first of all, a history of Bluetooth. Bluetooth didn't really start as Bluetooth. It started as just a wireless standard, 802.15.1, and this became adopted as Bluetooth 1.1 in 2002. And then the IEEE, who manages 802, kind of backed out of it and said, there's this great special interest group called the Bluetooth SIG, or BSIG, and they are going to manage this. So it's really a Bluetooth SIG standard today and not an IEEE standard, even though it started out as an IEEE standard long, long ago. Well, the 1.1 version of it had some limitations, and one of the biggest ones is it really didn't have a way to deal with interference, meaning that it would set up hopping channels because Bluetooth is a frequency hopping technology. So it communicates on a frequency set for a few moments, then it moves to another, then another, then another, and it cycles back through a hopping pattern. Well, the problem then is if one of those frequency segments had interference or something, then any data that was ever sent through that just didn't get through. So Bluetooth 2.0, which increased the data rate, hence enhanced data rate, but also added something called AFH, adaptive frequency hopping. And that's been there since 2004. And what AFH does is it basically detects that a communication didn't get through, and it says, okay, there must be interference there. We're going to stop using that. It's an oversimplification, but it's basically what it does. So this hopping pattern that it does through the frequencies it will adjust that pattern based on the fact that one of the frequency chunks isn't working. We're not getting the communication through, and we hit that one in the hop sequence. And so we're going to stop using that. And that's adaptive frequency hopping. Then in 2009, we had Bluetooth 3.0. One of the big things it added was something called plus HS. And basically what plus HS was a way to send data a lot faster. But the way it did it was it didn't really send the data over Bluetooth. It sent it over Wi-Fi. So this was dependent on a device being a Bluetooth device and a Wi-Fi device. Bluetooth could make the connection, but then data was sent using 802.11 so that we could get higher throughput with our actual data transmissions. Then the big one that impacts our discussion today was 2010 when Bluetooth 4.0 was released. This is when BLE got into the Bluetooth standard. Now, before that, there was development of this concept of BLE, though not called that, outside of Bluetooth. So this first version of BLE was really the rolling in of proprietarily developed systems outside of the Bluetooth process and incorporating those concepts into Bluetooth. So BLE first came about with 4.0. It was enhanced with 4.1 and other versions of Bluetooth. And then in 2016, we got Bluetooth 5.0, which enhanced it even further. But the big standardization enhancement really happened earlier this year with Bluetooth 5.1 in January of 2019. And that gave us AOA and AOD. Now, I'll get into specifically what that means a little bit later on, but it standardized locationing within the standard using these methods that are some of the best methods we have for locationing indoors and so forth in today's networks. So that gives you just a little rundown of where Bluetooth came from and how we eventually got to this thing called BLE or Bluetooth Low Energy. It certainly was not there in the beginning, and it's been around now for, well, about 9 years or so. So BLE is Bluetooth 4.0 plus, right? It was introduced in 4.0. It's been enhanced over time. So, what are some of the enhancements? Well, at first, there was really nothing in there for integration with IP connectivity, IPv6, IoT type stuff. And so that came along later in 4.1, 4.2, enhancements to Bluetooth 4.0. But it was designed with some specific things in mind. And the three big ones were low power consumption, low cost, and low bandwidth. So low power consumption was we want to be able to use things like small batteries that normally you might use these batteries in, well, I'll give you an example. Some of these low profile batteries, we use them in special Christmas tree ornaments that we have for our tree. So we've got these beautiful Christmas tree ornaments from, I believe it's Spode, that are these glass globes, and inside of them are these really pretty things, angels, snowmen, whatever, and they light up with multicolor LED lights. But you obviously want them to last through the whole Christmas season. And well, in this case, it uses enough battery power that pretty much that's all it lasts. And then I replace the batteries each year. But it's these low profile batteries that you utilize in these devices. Well, we want to be able to use a network communicating device with batteries that are very small. And there are many reasons for this, by the way. So the small battery is also part of the low cost factor. Smaller batteries tend to cost less in some cases, depending on the battery type, but they also have a smaller profile. So you need a smaller enclosure, right? So the smaller we can make an overall device, the less cost of materials to make that device. Okay. So you can think of it like that. So if I can fit everything in a little 1-inch by 1-inch device, and that is my sensor or my tracking device or what have you, then obviously costs can go down in production. So lowering cost of production is a big thing about getting many of these out there. We're over 10 billion, I'd say over 12 billion Bluetooth of some sort compatible devices that are out there in the world today. And to get more devices with sensors in them and things like that, we need to make sure that these sensors do not add to the size of the device that's already being built. So just a silly example, if I want a toaster that is able to be connected with BLE, I do not want that toaster to be bigger because of it, right? So I want to be able to fit it into the already existing size of my toaster. And that's one of the big things with low cost design concepts, keeping things small. And so by being low power, it means we don't need as many batteries, because if it wasn't for that, I could just put 40 AA batteries in a device and get a couple of years of functionality out of it, right? But I don't want to do that. I want to put one little battery in there and get a year or several years of life out of it. So low power consumption, meaning we don't want to have the radio consume a lot of power. Partly that results in low cost. And then, of course, to do this, guess what you're going to need? You're probably going to need low bandwidth, right? It is important to know that, with Bluetooth, there are many, many ways Bluetooth can be used. So Bluetooth can be used with higher bandwidth, which is going to result in usually shorter range and shorter battery life. It can be used with low bandwidth, which is usually going to result in longer range and longer battery life, or even low bandwidth with short range and even longer battery life. So it's all about how much power we need to consume, right? So these are big driving factors. Bluetooth 4.0 is really driven, BLE is really driven by specificity of use, meaning I've got a specific question, I need a specific answer. There's one thing I'm trying to do here. I might be looking for one metric real quick to make a decision. So it's not like I'm sending hundreds of megs of data and receiving hundreds of megs of data. A device using BLE that is actually transmitting data may come online only for less than a few seconds, even milliseconds a day, and get the answer to that specific question, and then take whatever action it needs to take, and then go silent again. So it's used for specificity. And really, if you think about the world of IoT, it's a lot of that, right? It's written separate from Bluetooth originally. So BLE was outside of Bluetooth, as I said, then it was rolled into the standard first at 4.0. 5.x is the latest version. We actually have 5.1, as I said, from January of 2019. And it is important to know, you'll see a term out there called iBeacon. iBeacon is roughly synonymous to BLE, and it's more of a marketing term that is used out there in the wireless space. Okay, so let's compare Bluetooth, since we've talked about these different Bluetooth. So when it comes to marketing, you've got Bluetooth, Bluetooth Smart Ready, and Bluetooth Smart. So Bluetooth is the old thing, right? It's what we use with our headphones. It's what you use for quick data transfer between phones or something like that. It was really all about set up a connection. Once connected, let's stream data, transfer data, what have you. Bluetooth Smart Ready says, okay, let's be old Bluetooth and let's be BLE. So it's one device that can do both things. Think a mobile phone, right? A mobile phone that is BLE capable is a Smart Ready device because it has the full Bluetooth stack for traditional Bluetooth, and it also has the BLE capabilities. And then there's Bluetooth Smart, sometimes called single mode because it doesn't do the old Bluetooth stuff, and it's really just designed to do the BLE stuff. So Bluetooth 4.0 and up stuff, right? And what this means is this single mode device, the Bluetooth chipset in it is probably more power efficient. And of course, then it's less capable as far as the amount of data it can push through in a period of time. It's going to have lower data rates. Okay. So Bluetooth, the old one alone, Bluetooth Smart Ready, the old one and the new one, and Bluetooth Smart, just the new one that's really, again, very focused on a certain thing. So I don't want to use a single mode chipset, something that is only BLE capable to do my wireless headsets and stuff like that. So you're going to see devices like laptops, mobile phones, tablets, they're going to have the dual mode capability. Whereas a sensor may only need to be BLE, right? So it can be much smaller, more power efficient, etc. And it's just going to have that capability. Okay, so with all of that, we need to talk a little bit of theory. I'm not going to go into the heavy math here today because this is a 101, but I want to familiarize you with some of the terms related to specifically locationing. Now, we have really 5 methods I'm going to talk about here today. We have RSSI, or signal strength, time of arrival, which is also sometimes called time of flight, time difference of arrival, angle of arrival, and angle of departure. Okay, so we've got RSSI, TOA, TDOA, AOA, and AOD. Now, the bottom two, AOA and AOD in the slide here, are in the newest BLE 5.1 standardized, okay? But AOA is really what you might call a multi-TOA, okay? And AOD, well, it's a little different. We'll talk about that when we get to it, okay? So RSSI and signal strength. what we do is we have multiple devices. Let's simplify this by talking about Wi-Fi access points. You have multiple wireless access points that see the signal from a client. We'll call these access points anchors. Each one of them measures the signal strength. Based on the signal strength they're each seeing, the central intelligence of this system can triangulate the location because of those different signals seen by different access points. Okay, so it's purely based on signal strength. Now, there are a lot of things that can impact signal strength, right? And wall attenuation can impact signal strength, things like that. So because of that, this is not going to give you as much accuracy as time-based systems. All right, so this is based on signal strength, but usually these RSSI systems could get into, 1 to a few meters of accuracy, okay? If you want less than a meter of accuracy, then you're dealing with TOA and TDOA. And by the way, that phrase, less than a meter of accuracy, sounds like you're getting less accuracy, but you're getting higher accuracy. So maybe I should say higher than a meter of accuracy, to be clear. So if you want to get into centimeters of accuracy, things like that, then you're going to have to leave RSSI. And RSSI is really not the one that's used by most systems today, but it is a locationing method that is available. Time of arrival is where the distance is calculated between each anchor and a device. So by sending from a device to the anchor, from the anchor back to the device, etc., we can figure out the time of arrival. And so each anchor calculates that with the device. And then we take that information to triangulate. Now, the reason this one is chosen by some is because there's no time synchronization required between the anchors. The time synchronization just has to happen between each anchor and the device. The time difference of arrival, all of the anchors must be synchronized in their time because all they're doing is looking at the signal received at each anchor, and the time difference of that same received signal at each anchor is used to triangulate. So those anchors obviously have to, among themselves, be very perfectly timed. So different vendors will make their argument about why TOA is better than TDOA or TDOA is better than TOA. They'll make their arguments, but the point is that each anchor is what you might call a single angle of arrival anchor, and that's what they're using. So they're using just a single signal that comes in, and the time that it takes for that signal to travel from the device to the anchor. And then we triangulate based on 3 or 4 of these different anchors that have that information. Now, AOA is looking at the angle of arrival, and it's an array used at the anchor. So this can be extremely precise. Because of this, it can be extremely precise in the information that it gathers. Because it's using an array to capture this information, right? Instead of just a single antenna or looking at it in a singular concept. And we'll look at this in an example in just a moment. So you could call this multi-TOA, right? Because it's really using multiple antennas. So when you think about locationing is based on what the antenna sees. And if you have more than one antenna that sees, you can get more information. You can think of it like the difference in depth perception you have if you cover one eye. And if you've ever noticed that when you cover one eye, your brain no longer has an AOA. Your brain now just has a TOA. And so your brain is now looking at that object with a lot less ability to do calculation. And it's not triangulation, it's more biangulation, but still it has less ability to do that. Just imagine if we had 5 eyes, it'd be even better, wouldn't it? Would we still call that beautiful? I'm not sure. But anyway, that is a way to think of it. When someone lacks sight in one eye, they lose some of their 3D perception because they have lost the ability to do biangulation. And so that's one of the areas where you could say that the anchor can see better when it uses an array of antennas instead of using just one antenna. Additionally, when using an array of antennas, a single anchor locationing system can be more accurate than a single anchor locationing system just using TOA. So in other words, if you're trying to do locationing with just one AP, with just one anchor, then obviously you can get more accuracy if there's an array in that anchor than if there's just a single antenna in that anchor. Okay, so that's a simple way to think about that. Now, AOD happens at the client. It's based on multiple signals from the anchor from different array antennas. Now, keep in mind, I'm keeping things simplified here. More details will follow in later webinars, as well as in the CWSA and other materials. So this allows the client, the device, to determine where it is. And it's able to do that based on looking at multiple signals coming to it from an anchor, okay? So let's illustrate some of this to kind of drive the point home. So AOA, angle of arrival. I've got a single anchor here on the left, and I've got a device. The device sends a signal, and we measure T1, T2, T3, T4, T5. I'm just giving these examples. It may measure 3 times of arrival. It may measure 4 times of arrival. It may measure 2. It depends on the antennas in the array, right? The point is the measurement location is at the anchor. And so I've got multiple points of measurement, and you might think, well, yeah, but these antennas are going to be really close together. But remember, think about the old days of Wi-Fi. Remember the good old Linksys WAP54G or WRT54G had 2 antennas sticking up out of the back of it, right? Why were those 2 antennas there back in an old 802.11g time frame and even 802.11b before it with the WAP11 and the WRT11? Well, the reason was for diversity. So those antennas just a few inches apart could get a very different quality of signal on reception. Well, in the same way, just a few inches or even portions of an inch apart, these antennas can get different measurements, and based on those different measurements, we can help to determine the angle of arrival, the angle at which the signal's coming into the anchor from the world around it, right? And so this is how we can measure at a single anchor with more accuracy the direction from which the signal is coming. So if you think about it, if you've got an antenna that's a single omni antenna, I have no idea where the signal's coming from. I really don't. I have literally no way to know where that signal is coming from with just one anchor. But with this, with one anchor, I can get an idea of the direction of the source of the signal. Now, keep in mind, there's reflection indoors, right? So if I'm in a huge wide open space outdoors, this can be really pretty accurate as to location just with one anchor. But indoor, it's helpful to have multiple anchors because I have reflections. And it's just because I know the signal came to the anchor from a particular location doesn't mean the device is in that direction, right? So that can be an impacting element, but there are algorithms even to deal with that at a single anchor. So that is AOA. Now AOD is the other direction, right? So of my antenna arrays, I can send out signals from different antennas in the array. The client device can see the phases of those different signals and use that information in order to self-locate, in order for it to determine where it itself happens to be, okay? Again, these are oversimplifications, but I want to get the gears going today. I want to get you thinking about these concepts, the math behind this stuff and so forth. We'll be talking about those later. In fact, I'm starting up doing a series. I've just talked a little bit about artificial intelligence in the news desk. In future news desks that are released, I'm going to be getting into different algorithms and the math behind those algorithms and so forth. And some of that will include some of these kinds of things, locationing eventually in the future. So let's get into the last thing I want to talk about with locationing now that we've talked at a high level about some of the locationing methods. Some tips to help you right away as you begin getting into these things. The first one is height matters. Okay, what do I mean by this? Well, sometimes we don't really think about this, but if your locationing algorithms are based on time it takes for RF energy to get from point A to point B, then the higher my anchors are on the ceiling, as opposed to the devices I'm locating on the floor, the less accuracy I'm going to get. So to give you an example, a 20-foot high sensor results in only a 3% change in location when a device actually moved 5 feet. Okay, so the result equals lower accuracy with higher placement. This is why you'll hear people saying, you know, ideal is 10 feet, 12 feet, 15 feet. You get higher than that and you run into problems. There are all kinds of strategies that people use. So for example, in warehouses that are 40 feet tall, rather than mounting them way up on the ceiling, they may have extender poles that come down that the anchors are mounted on. They may mount anchors on the walls part of the way up instead of all the way up on the ceiling. Height matters because it makes it so that a Horizontal move, since you're dealing with signals going up vertically to the anchor, a horizontal move is seen as less movement by the anchors. So that's a key factor. Height does matter. Keep that in mind. Algorithm matters. So the algorithm that's chosen matters. AOA, I like to call it multi-TOA, but that's just to simplify it. There's more complexity to it than just that. But AOA is better than uni-TOA or single TOA, which is better than RSSI. So what algorithm your system is using is going to matter. So you want to make sure that you have a good locationing algorithm. Of course, you're not the one creating it, but you need to make sure your vendor implements one that gets you the location accuracy that you need. And that's the big thing you're looking for. What is the level of location accuracy I can get? And in addition to the level of location accuracy, what is needed to get that? So a vendor might say, you can be accurate down to 10 centimeters. Okay. Well, what do I need to accomplish that? How often do I need anchors or the central sensors, the APs, or whatever they happen to be calling it, depending on the system? So how often do I need those anchors spread throughout my facility? And that's going to impact, obviously, then, right, the cost of deployment to get that level of accuracy. Device support matters. So remember, 5.1 is really new. This is what standardized AOA, even though some vendors proprietarily do something like this, right? So what devices are out there right now that support Bluetooth 5.1? Well, almost nothing, right? Because it's just a few months old. So device support matters. You have to make sure your devices can give to this anchor system what it actually needs to get the job done. And then the final tip that I'll give you is the floor plan matters. Okay, so the one thing I've left out of all this so far is, if you think about an anchor and it's just somewhere above me and I'm somewhere below it, how does it know where I am? Okay, all it could really do is say you're this far from the anchor A. So if you've got anchor A, B, C, and D, right? And they work together, they look at a device, and all they could do is say, you're this far from anchor A, this far from anchor B, this far from anchor C, this far from anchor D. That's all they could tell you if they didn't have something else. And that's a floor plan. Okay. So they need a floor plan, and they need to know two things. Where are they on that floor plan? And what is the calibration of the floor plan? In other words, when you import a floor plan, accuracy is key. The floor plan has to be right, first of all. There can't be rooms that exist that aren't on the floor plan. And the calibration of that floor plan has to be right. So I can't say, well, on the floor plan, there's a space that is 10 feet and I've mapped that as 8 feet. That's going to greatly throw off all of my locationing everywhere, right? So accuracy is key. I need a floor plan. The floor plan needs to be right. And the anchor needs to know where it is in the floor plan. Otherwise, it can't determine where devices are within that floor plan. Okay. So very key things that need to happen. So these are some tips that matter to make locationing work. Now, again, we're going to be getting into more things on locationing in the future. We'll be getting into Bluetooth in more depth, both from a data standard and a beaconing standard and locationing standard and things like that, and other technologies as well as time goes forward. So as we continue to move into Wi-Fi and the rest of wireless, we'll keep exploring the rest of wireless to see what is out there and why it matters to those of us that maybe have specialized in Wi-Fi, because specializing in Wi-Fi is going to become less and less rare in the coming decade. You're going to need to know Wi-Fi really well, because for the next decade, it's going to continue to be the primary data transmission standard that we use for business communications, from laptops, tablets, mobile phones, and many other devices. Of course, with the exception of when mobile phones and other devices use LTE or 5G. But when it comes to our networks that we deploy and build, Wi-Fi is going to continue to be the main thing we use to send lots of data. But there are many other things we're doing now. We're doing locationing. We're making it so that as customers walk through the store, their phone gives them notifications of specials that are going on in a 3-foot radius of where they are right now, and things like this. We're detecting that they go down an aisle every time they come into the store, but they've never purchased anything from that aisle, based on customer loyalty programs. If you didn't see, I had air quotes in the air there. You couldn't see it. But the point is that we know they've gone down that aisle. They've never bought anything in that aisle. How can we motivate them to? Well, maybe when we've detected they've done that 10 times in a row, next time they go down that aisle, we automatically send to the app on their phone a coupon that gives them 30% off of the top seller in that aisle to get them to buy it once so that maybe they'll buy it again in the future. I know that stuff all sounds big brother and scary, but it's being done. These are the kind of things that are being done, and more people need to know how to support these technologies and use them. So with that, that's what we have scheduled to cover today. I want to thank you for attending.